Okay, so I decided to create this slide, um, and I'm hoping that it will turn into a series, and this is just the first part of the series. So with this particular series, I hope it kind of like builds up like a game, kind of. Um, but yeah, anyways, so this is called Logic 1, brought to you by Cafe, of course. I have the Calico critters on the background to kind of like resemble your name. But yeah, let's begin. So let's start constructing our language. We'll call it L subscript 0. And to begin like the syntax of our language, we're gonna have two main things. We're gonna have a set of propositional variables, and we're gonna have a set of logical constants. Logical constants are what creates or what makes or breaks your sort of logical vocabulary. Um, and so the five main logical constants we're going to be concerned with in this language is going to be the and. So the and will be the ampersand, uh, the or. So that's going to be the lowercase v right here. The if then, that's going to be the right leaning arrow, and the if and only if, that's going to be the one that kind of looks like the if then but going both ways, and then the not operator, which looks like a squiggly line. Their conventional formal names or formal labels are the conjunction for and, disjunction for or, the conditional, or you can also call it implication for the if then, the equivalence for the if and only if, and negation for the not operator. Okay, uh, let's provide our language a semantics. We're gonna give it what's called an interpretation. It's a function that maps a certain formula, or that maps certain true values to a formula, or maps a formula to a set of true values. So we'll represent that with a italicized V to sort of stand for the interpretation function. So for some formula A, uh, we're gonna give it two true values. So this is what our language is going to be Boolean. It's gonna only have two true values, and these true values are going to be 1 and 0, or respectively true or false. You could also represent that by T or V. I mean T or F, but either works. And now we want to extend our interpretation to complex formulas. So the way we would do that is, so basically, the way we would do that is take whatever operator we want, we're appending to the formula, and basically give it a certain definition. Now, there's what's called truth table definitions of the connectives, which is a lot more visually clear. But for now, we're just going to stick with this sort of definition here. So the interpretation of not A. Also, here's a quick side note. The negation connective is the only connective that can take only one propositional, that can only take one formula, whereas every other connective takes multiple formulas, or takes two formulas. So not A has the true value of 1 if and only if. So if the if with two F's means if and only if. If and only if the truth value, or the interpretation of the atomic formula A is 0 or false. So all that basically says is that what the negation connective does is basically just gives you the opposite value of whatever you have. So it gives you, so if like A were to have been true, then appending a negation to it will give you 0 or false. So it basically just does the opposite of whatever. Okay. So the interpretation of A and B is true if and only if the interpretation of A is true and the interpretation of B is true. And all this is saying is that the formula, the conjunction formula, can only be true when all of its parts, all of its conjuncts are true. Hence why it's a true functional connective, because it's a true function of its parts. So if A is true and B is true, then the conjunction A and B is true. But if A is false and B is true, then the conjunction is false. Hold on. And also, if A is false and B is false, A and B is still false. A and B is still going to be false. Okay. So the interpretation of A or B is going to be true if and only if A is true or B is true. So what this means is, whereas with and it's a lot more stricter as to what counts as a true interpretation, disjunction is only false when both A and B are false. That's the only time when it is false. And for this specific interpretation of OR, we're thinking of an inclusive OR. There's also what's called an exclusive OR, but we're not going to get into that. There is also the interpretation of the conditional A implies B. And that's true if and only if A is false or B is true. And the reason why it's this particular definition, it would make sense when you realize that A here is a sufficient condition for B, and B is the necessary condition of A. So let's think of a conditional. If it's raining outside, then the ground is wet. If A is false, right? If the ground is not wet, if A is false, if it's not raining outside, that doesn't mean that the ground can't be wet. It can be wet for other reasons, right? But what this is saying is that there's a particular link that's established when A is true. So when the sufficient condition is established, then it follows that the necessary condition obtains. But a necessary condition can obtain either way. It doesn't particularly depend on the sufficient condition, if you get what I mean. Okay. And the interpretation of A, if and only if B, it's basically a conditional that goes both ways. So think of the equivalence as an equal sign, but instead of saying that two things are equal, it's saying that two things are equivalently true or equivalently false. So the interpretation of A, if and only if B, is going to be true if and only if A is true and B is true as well, or the interpretation of A if and only if B is going to be false, is going to be true also if, hold on, it's also going to be true if A is 0 and B is 0. So all it's saying is that so it's basically saying that the equivalence is basically saying that it's going to be true if the values of A and B are the same. So it's kind of a mix between the conditional and the conjunction. Whereas the conjunction is false if A and B are false. The equivalence is true if A and B are both false. So as long as A and B have the same value, the equivalence is going to be true. I hope that makes sense. Okay, now the how-tos. How are we going to apply this language? So let's have like a regular English sentence like Zoe drank every coffee. Let's call it sentence A. We're going to map sentence A into capital A, which is the set of all propositional variables. We're going to give it the value of one propositional variable. So we're going to transform that into P. And P has an interpretation of A or 0 in our language. So let's say that we want to extend this into a complex formula. A1, Zoe did not drink every coffee. We're gonna append the not negation to P, and if you recall, what's the definition of not? It's the opposite of A, or it's the opposite of what it's negating. So the truth values of not P is going to be 0, 1, just changing the order. And let's say like we have another sentence, Joe drank water. We're gonna map that into Q. Let's combine A and B into a conjunction, P and Q, where P is true and Q is true. Okay, here's a question for you. What is the truth value of P and Q? Remember the truth, the definition of and. Okay. Now, what are the limits of our logic as of now? Let's take into account our sentence from earlier. Zoe drank every coffee. Well, there's two ways we can negate this, actually. We can negate it internally by saying Zoe did not drink every coffee. We could also negate it externally by saying it is not the case that Zoe drank every coffee. And both can be translated in our language as of now as not P. But both are not exactly the same. When you say it is not the case that Zoe drank every coffee, you're negating the sentence as a whole. When you say Zoe did not drink every coffee, you're not negating the sentence as a whole. You're negating only some part of the sentence. So we want a way to so our language right now, we can't support distinctions inside of these propositions. So the only way we can do that is if our language is able to deal with quantification. And that's where later logics like first order logic and second order logic come into play, because they can deal with quantification. But yeah, this is like the limits of our language right now. In the next video, hopefully, I'm going to be talking about what are called the transformation rules of our language. The transformation rules are what allows us to do certain what allows us to do certain implications and entailments within multiple lines of propositions. Okay.